look at lesson 2.1, an introduction to tangent lines. And we're going to be writing equations of tangent lines using tables and finding instantaneous velocity using tables. So today's focused on the strategy of using tables. It's not the most effective strategy or the most efficient strategy, but it is our first strategy. So let's define what a tangent is first. A tangent is a line that has the same direction as a particular curve. So if we zoom in really well right here, you can see at this particular spot, it is a point of tangency. And the reason it's a point of tangency right here, because the steepness of my parabola and my steepness of my line match up perfectly. You can see on my circle, that's where you probably have remember hearing the word tangent before because you had them with circles in geometry. Right at that, and when we define tangent in geometry, we refer to it as a line that only hits it once. And that's true about with a circle. It's not always true with other curves though. So really, the idea here is that the slope of this line and the slope of that circle is exactly the same at that particular point. You can see that there, how this steepness is matching up. Okay, and here, this bottom graph with this almost sine curve-esque. On the sine curve, you can see how it's intersecting it. So a tangent line is a line that has the slope of the rate the graph changes at that particular point. So on here, this particular graph, I'm going to switch to highlighter. Right here, it's considered a tangent line. But even though it intersects the curve again over here, that is not considered a tangent line there. It's only considered a tangent line with that point in reference to that point of tangency that determined the slope. A secant line, okay, is a line through a point of tangency. So it's still through this same point of tangency, but it's a second point on the curve that we're working with. So our secant line here is like from there to there, and our tangent line only intersects the curve at that one point of tangency, okay, and it has that same slope. So here on this parabola, as I move the point of tangency, you can see how the slope is changing, okay, and the tangent line also changes. So let's find a tangent line together. So here I have y equals x squared, and I want at the point 1, 1 for my point of tangency. So let's insert another point, and I'm just going to call it a generic point. I'll place it right here of x, x squared. So I have this point of 1, 1, and my other point of x, x squared. As I look for this, our slope is going to be change in y over the change in x. Okay, so change in y is going to be x squared minus 1. Change in x is going to be x minus 1. That's what the slope of this line, of this P, point Q, the slope of from point P, point of tangency, to point Q. We all right so far? So, depending on what I'm making the x value, it's going to give you obviously different slopes because these are basically like on here, this is a secant line, okay? But if I place Q a little bit closer, it's another secant line, but it's going to be closer to the line of tangency, okay? So if I evaluate for assorted values of x, so let's say starting at 10, well, our slope would be 10 squared minus 1 over 10 minus 1. So you get 99 over 9, which is 11. But that is very far away. Okay, so let's move closer. if I make my x 5, we'd have 5 squared minus 1 over 5 minus 1, so we get 25 minus 1 is 24 over 4 or 6. Okay, see how my slope is less drastic? Well, that's because I'm using points closer. Now let's try maybe 2. So we get 4 minus 1 over 2 minus 1, so our slope is 3. And we'll try 1.5, 1.2, and 1.01. So I'm going to try these. We'll have, when we plug in 1.5, get a slope of 2.5. When I plug in 1.2, I get a slope of 2.2. As I plug in 1.1, I get a slope of 2.1. And when I plug in 1.01, I get 2.01. So as this x value is approaching 1, what's happening to my slope? Well, you can see my slope is decreasing, and as I'm getting closer, there's smaller and smaller decreases, and it appears to be approaching 2. Okay. You can also look at it from the other side. So instead of having 1.01, it's also a good habit to look at like 0.99 and 0.9 and approach from the other side as well. All right, so this is what's called a limit, the value that a function or sequence approaches as the input or index approaches some value. And yes, in this case, the limit does exist. Thank you, mean girls. So the slope of a tangent line is the limit of the slopes of the secant lines. So as the point gets closer, okay, so as I slide that second point for my secant line closer to the point of tangency, the closer it is to the tangent line slope. And as it gets closer, it's obviously going to approach that slope. And you could see that with our table, how as I increased it, it got closer and closer and closer to 2. Whoops. As we were approaching 2. All right. Boom. So for this particular problem, we're talking about the limit as x approaches 1, because that's where we were approaching. We were getting closer to that point of tangency of this slope, which was x squared minus 1 over x minus 1, and that limit came out as 2. So then, to find the equation of the line, we're going to use point slope. So our slope was 2, and the point of tangency was 1, 1. So I'm going to literally just plug in the slope. And you could simplify it to slope-intercept if you want, but most of the time we just leave it in point slope, just like that. Okay? You try the second example. So pause the video and try it out. Try to find the equation of the tangent line for y equals x cubed at the point 2, 8. You paused it and tried it? Okay. So our other mystery point is x comma x cubed. Then I'm going to find the slope of the secant lines. That'll be, and you could actually do it as 8 minus x cubed or x cubed minus 8. It just looks a little weird to have first. X cubed minus 8 over x minus 2. We're doing the limit as x approaches 2 of x cubed minus 8 minus 2. So this is what my tangent line slope is, m tangent. So that's telling me the slope of my tangent lines. Okay, so I'm going to find a bunch of secant line slopes, and that's going to help me approach it. So this is going to be my x, and then my slope will be here. And so if I'm approaching at 2, I might do like 3, 2.5, 2.1, maybe like 2.01, 2.001, And we'll do it from the other side too. 1.999 and 1.99 and maybe 1.9. So since this is a lot of calculating, I'm going to show you how you can do this on the graphing calculator. First things first, I would type in what I have here. I have x cubed minus 8 divided by x minus 2. So I'm typing the slope into y equals to do this a little bit quicker. Okay, and then I'm going to go second graph. It gives me the option here. And actually, we'll go to my table set. So if you hit second window, most calculators default to both of these independent and dependent as auto. We want independent to be on ask for this. If our independent is on ask, when we go to the table, it'll give us a blank table, and I can type in 3, and I can type in 2.5 and 2.1 and 2.01, 2.001. Okay, and I could also type in 1.999, 1.99. Okay, and you can see there's that same table all done out for me. Whoops. Okay. Okay. So when we approach, again, really the 3 isn't even that helpful at all. The part that we're really more concerned about with is right here from either side of that. Where are we getting closer to? And it appears that we are approaching. Dun, so my slope is 12 and my point of tangency is 2.8. We'll have y minus 8 is 12 times the quantity x minus 2. Okay, so velocity is what we're going to talk about next. And velocity is very, very similar to what we've just been doing. Okay, so suppose a ball is dropped from the roof of the Empire State Building. That's 381 meters tall. The free fall distance is given by the function s of t is equal to 4.9 t squared. When we go to find an average velocity, it's the distance traveled divided by the time elapsed. Sounds like a slope to me. Okay. So time interval. So if I'm looking at 5 seconds, how fast is the coin going at 5 seconds? That's my goal to find. Okay. I would do an interval that would be like maybe from 5 to 6 seconds. And then I'll do a smaller interval that's like 5 to 5.5 seconds. And then we'll do like 5 to 5.1 seconds. And then we'll do like 5 to 1. Last but not least. Okay. So when we're doing this, the distance traveled, well, that would be like on the time interval from 5 to 6 would be 4.96 squared minus 4.95 squared. Okay, that's the change in the distance. So the distance traveled. And on the bottom, I'm going to have 6 minus 5. Okay, so my average velocity on that one comes out as 53.9 meters per second. Okay, so fill in the rest of this table and then use that to estimate what the instantaneous velocity. Okay, these average velocities are over an interval, sort of like how our secant lines were 2 points on the curve. The instantaneous is at that one moment, similar to the point of tangency. Okay. And this concludes lesson 2.1.